I would also like to thank the organizers for having me here. So my name is Yi-Kai Liu. I work at NIST, and I'm going to talk about tamper-resistant cryptographic hardware in the isolated qubits model. So I would like to describe to you an approach for using quantum devices to realize some broad class of cryptographic functionalities. And so this is something I've been working on in the last couple of years. And I think there are many avenues for further work along these lines. So I hope to get you interested in this. So here we're going to talk about realizing tamper-resistant cryptographic devices. And so one example of such a device that has been studied in theory is something called a one-time program. A one-time program is a computer program that can be run exactly once on an input of your choosing, and after that it stops working. And it has the additional property that the intermediate results of the computation are hidden. So it really operates like a black box. You choose your input, feed it in, and out comes the result, but you don't see any of the intermediate steps. And so this is related to program obfuscation or software copy protection. But it's important to point out that this is a functionality that really requires a combination of both software and hardware. If you had only software, you could always run the program more than once. So to achieve this one-time requirement, you really need some kind of hardware. So I will describe to you a particular approach for trying to realize these one-time programs based on a physical assumption. And so this proceeds in a few steps. So the end goal is to build these one-time programs. Now these were first studied by Goldwasser, Cayley, and Rothblum, and they showed how one-time programs can be realized from a simpler primitive called one-time memories. And a one-time memory is sort of like a device that does non-interactive oblivious transfer. And they showed that if you could build these one-time memories, which seem much simpler, then you could realize this general one-time program functionality. So my work has been about ways of building these one-time memories using quantum systems. And I was sort of motivated by in particular work on solid-state nuclear spins. And so these are single qubits that can have long coherence times, but where it's relatively difficult to do multi-qubit entangling operations. And so this is some family of devices that exist in the lab. And in order to be able to reason about it formally, so I propose an abstract model called the isolated qubits model, which gives a clean mathematical description of this type of device. And then within this model, I propose some constructions for one-time memories and proved that they satisfy some notion of security. All right, so this is sort of the project that I've been pursuing to try to take one-time programs and then realize them and eventually be able to connect them to some physically natural assumption. Now, just at a high level, it's interesting to ask, so why is quantum information even relevant here? Because people, of course, have tried to build cryptographic devices from classical physics alone. And so in fact, quantum information is useful because it has properties such as the no-cloning theorem or these measurement disturbance trade-offs, which seem relevant to constructing one-time programs. Now, it's actually much more subtle than that because, as many of you will know, there are these impossibility results for quantum bit commitment and quantum oblivious transfer. So in fact, in a fully quantum world, we cannot realize these kinds of functionalities with information theoretic security. And so this is why things like the isolated qubits model become interesting, that you need quantum mechanics, but you also need some additional assumption to make these kinds of cryptography possible. Okay? And so that's the high-level view of what this talk is about. So on a technical level, there are basically two results that I will try to describe to you. So the first one is a construction for one-time memories based on an old idea due to Wiesner called conjugate coding. And so this conjugate coding idea by itself is not secure against quantum adversaries. And what we show is a particular concrete instantiation of conjugate coding, which we can prove is secure against a natural restricted class of quantum adversaries. So these are adversaries that can do multipartite LOCC operations. So they can do single qubit operations and classical communication between qubits, but no entanglement between qubits. And so this is the isolated qubits model, essentially. And so this construction has several desirable properties. You can prove that it satisfies a natural notion of security, a sort of single-shot security, where the adversary's uncertainty about the contents of the one-time memory is quantified using the smoothed min entropy. And so this is roughly what one wants for cryptography. And you can prove security against general LOCC adversaries, and you can actually make the whole construction efficiently implementable. So you can make it so that the honest parties only all run in polynomial time. Now, so one difficulty with this construction is that it leaks some information, that you cannot prove that it has perfect security. It's possible, for instance, for the adversary to gain partial information about different parts of the secret, which in an ideal situation he should not have. And so this sort of makes a connection with some of these earlier discussions today about leakage-resilient computation, that here we have a leakage problem. And so the second result, which I will present, is a way of dealing with this leakage using privacy amplification. Now, so privacy amplification will be familiar to you from work on quantum key distribution, but this setting is actually a bit different because in QKD you have interaction, and so you have the ability for Alice and Bob to choose a random seed and then use a randomness extractor and arrange things so that the seed is unknown to the adversary. Now, in our setting, it's not interactive, so we actually cannot do this. Whenever we use a randomness extractor, we have to assume that the adversary will know the seed for the randomness extractor and can use that in his attack. And so we need something a bit different. And so what we can actually do is we can do a kind of deterministic privacy amplification that uses a fixed hash function. And we can prove that this is secure using the LOCC restriction on the adversary. So because the adversary is restricted to these LOCC operations, we can actually do fully deterministic privacy amplification. And so this is the second result that I will describe to you. And so between these are some progress towards building one-time programs in the isolated qubits model. So that's the technical content of the talk, but somehow there's also a non-technical message which I want to convey, which is that isolated qubits are fun. And so they can be fun for different people in different ways. So for theorists, I think they're interesting because they're a different model where you can do many interesting kinds of cryptography. And because the known constructions already do interesting things, but they seem very far from optimal. So everything that I'll show you depends on fairly simple probabilistic constructions and relatively crude bounds. And it seems like one should be able to do much better than this. So for experimentalists, this is interesting because this isolated qubits model describes some other class of special purpose quantum devices which one can try to realize. And so these are quite different from quantum repeaters. These are single qubits where one wants to have long coherence times and good single qubit operations, but one does not want to do entanglement swapping. In fact, one never wants entanglement swapping to happen in this system. And so it's simply a different kind of device which one can ask whether this can be built. And so this could be another step along the road to building large-scale quantum computers. This could be another kind of simpler device which we'll realize along this path.
I'm going to check something just.
Sorry.
Okay, thank you.
Sorry. Okay, so with this talk, I'll give an overview of some of these ideas about one-time memories and how they're used. And so the first half of the talk will be fairly conceptual. And then the second half will be a bit more technical, and I'll show you how one actually gets some of these results in a more detailed way. Okay, so just to be very explicit, so a one-time memory is a device which can be programmed with two messages. S and T, in such a way that the adversary can read either one message, S, or the other message, T, and he has a choice, but he cannot learn both messages. So this is like oblivious transfer. And so I'm going to start at the highest level. So our end goal was to produce one-time programs. And let me describe one way of getting these from one-time memories. So this is purely a classical construction, but it's quite nice, and it's just good to keep in mind. So the way you do this is using garbled circuits. And so the way we'll implement a one-time program is by providing a collection of one-time memories, as well as a collection of classical data, which consist of encrypted ciphertexts, encrypted using different combinations of keys. And the idea is that, this is the original circuit that we want to compile into a one-time program. And so for each input wire, we will have one-time memory. It will contain 2 keys. And those 2 keys correspond to the 2 possible settings of that wire, either 0 or 1. And then again, we'll have these ciphertexts. And so kind of the easiest way to understand how this is constructed is to look at how it should be used. So if the user wants to choose inputs x equals 0 and y equals 1, he should open each of these one-time memories in the appropriate way so he gets the corresponding keys. And then he should look at all of these ciphertexts, and it's set up so that exactly one of these ciphertexts can be decrypted using the keys that he has. And so this will give him another key inside. And this key will give him the information that he needs to evaluate the next gate in the circuit. And when he finally comes to the end, then the answer will simply pop out in plain text from this process. All right? And so this is a simple idea, and it's easy to see that all of the intermediate stages in the computation are hidden because they're encrypted. And it's easy to see that the user can only run the program once because each time after he finishes reading the one-time memories, they're finished. He can't get any more information. Okay, so this is the idea. Proving security of this is quite complicated on its own because this is a somewhat complicated scenario and you can have rather sophisticated adaptive attacks. So it's not entirely straightforward to prove that this is secure, but at least the construction is very natural. Now we've reduced our problem from building one-time programs to building one-time memories. And a natural way to do this is using conjugate coding. So let me briefly remind you how this works. So the idea is to encode 2 classical bits into a single qubit. And you want to do this in such a way that if you measure in the standard basis, the outcome is correlated with the first bit. And if you measure in the Hadamard basis, then the outcome is correlated with the second bit. And so you do it by using these states that are sort of intermediate between the standard basis and the Hadamard basis. And you work it out, and this is what you get. Okay, and so to really do this without error, you actually need to do it with many qubits and longer messages, and you use an error-correcting code. So you take 2 strings S and T, you apply some classical error-correcting code that gives you these code words, C of S and C of T. Then you pair off the bits of the code words and encode each pair of bits into a single qubit. And so if you're playing honestly, then if you want to recover the first message, you measure in the standard basis, you get a noisy, corrupted version of the code word C of S, and then you run the classical decoding algorithm. And if you want to recover the second message, you do the same thing, but in the Hadamard basis. And so the bad news with this construction is that, in fact, if you can use an entangled measurement, then you can recover both messages. And you can see explicitly how you can do this. So if you want to recover both messages, you can run this classical decoding algorithm in superposition. So you don't collapse you don't actually do any measurements. You simply do this decoding operation in superposition. This lets you recover, say, the first message S. You can copy that out because you get the message with high probability. You can copy it out without damaging the state very much. Then you can uncompute everything, now run the decoding algorithm again in the Hadamard basis and get the second message. Okay? And the thing that you would notice is that for many choices of this code C, this decoding operation actually is going to generate quite a lot of entanglement because it's going to involve computing some complicated function that depends on all of the qubits, and you have to do it in super precision, so you're producing entanglement. And so this is sort of an interesting fact that the honest players in this scenario don't need entanglement, but the adversary, in order to break it, does need entanglement. And so this is the idea that we're going to try to exploit. So one can define this isolated qubits model where you have single qubit operations, you can't generate entanglement, and so this is nicely described by LOCC adversaries. And this is sort of modeled on nuclear spins and solid state materials, and these are easier to build than quantum computers. And so one important point is that a scheme like this can still be secure in a world with quantum computers. It's perfectly okay for the adversary to have a quantum computer. He simply shouldn't be able to teleport information in and out of an isolated qubit using the quantum computer. All right? So this is the model. And our intuition and what we'll eventually show is that this conjugate coding scheme actually is secure in this model. That entanglement is not only sufficient to break it, it's also necessary to break it. And so this has some connections to earlier work on non-locality without entanglement. And essentially this is saying that you can have operations that are reversible in quantum mechanics, but which seem irreversible to players who use only LOCC. So it's possible for you to do some transformation using LOCC, which is irreversible using LOCC, but can be undone using an entangling gate. And so this is kind of interesting, that this is a way of exploiting the power of quantum entanglement without actually having to generate entanglement yourself. You just make the adversary have to generate entanglement. And so this is kind of cute. So this is also related to earlier work by Salvai on quantum bit commitment using k-local adversaries. So these are adversaries who can entangle at most subsets of k qubits at a time. And so these much earlier works indicate that this kind of thing is actually possible in a number of different scenarios. Now, the exact way that Salvai's protocol works doesn't quite apply here, because in his protocol he required some kind of interaction between the parties, whereas this setting with one-time memories is non-interactive. And so kind of the functionality that we're trying to realize here is a bit different from what has been done previously. And then, so you can also compare this to other models like the quantum bounded storage model or the noisy storage model. And again, these are different kinds of assumptions one can make about an adversary. And one can also try to combine these different models. So one can try to design protocols that are actually secure in more than one of these models simultaneously, so that as long as the adversary obeys at least one of these assumptions, then the model is secure. And so this is kind of an interesting direction. And so there's been related work also on quantum tokens, which are again using some simpler ideas using single qubits to realize quantum money. And there's been some work on password-based authentication, or password-based identification, which also aims to be secure under similar assumptions. Okay? So this is sort of the high-level overview. So actually, I should pause at this point and ask if there are any questions. Okay. So next I'll show you some more technical things about how you actually build these one-time memories. And so the way I'm building them is really in two steps. So first you construct a leaky string one-time memory. So this is a device that stores 2 strings, and it has this leakage behavior that it can keep secret a constant fraction of the bits, but it leaks. In principle, it can leak the remaining bits of the messages. And then, so using this, so we can build these using conjugate coding in a more or less straightforward way. And then combining this with privacy amplification, then you can get something which is much closer to the ideal device, which stores a single bit and leaks only an exponentially small amount of information. Okay, so I'm actually going to start with the second step because the second step is much more recent work, and it's sort of, I think, so we can take it for granted that there's some way of doing conjugate coding and choosing the code so that this will actually be secure in this leaky sense. And I'll show you how you can do privacy amplification on top of that. So yeah, so this is the definition of leaky security. That so you store 2 messages S and T, each one is L bits long, and assume that they're uniformly distributed just for simplicity. And in the constructions that we'll use, this will in fact be true. So this leaky notion of security is that for any LOCC adversary, if Z is the adversary's output, then the smoothed min entropy of S and T conditioned on Z is at least some constant fraction times L. In the bounds that we show, it's about 1/2. And so this is this is lower bounding the joint entropy of S and T, but if you use entropy splitting, then this will tell you that that probabilistically there's always going to be one of the 2 messages which at least has roughly 1/4 times L bits of uncertainty. Okay? And so what we want is to do privacy amplification on this. So the way I'm going to do it is to choose 2 R-wise independent random functions, f and g. So these you can think of them as hash functions. They map L-bit strings to single bits. And R-wise independent means that if you look at correlations of the values of the functions on R different points, that these will look uniformly random. So 2-wise independent hash functions are the more familiar kind that show up in many cases. And here we're going to have to choose R larger to be some polynomial. And so these are sort of stronger devices than are usually used in privacy amplification, but in fact we can still implement these efficiently in polynomial time, provided that R is at most polynomial in the security parameter. Okay? And so the key thing is that actually these we have to fix them permanently as part of the construction. So they're set once and for all. And we want to assert that with high probability over this choice, the one-time memory will be secure against all possible LOCC measurements that the adversary can do. So this is uniform security in some sense. Okay, and then, so now how do you use these functions? Well, here's one sort of simple way of doing it, that if you have 2 bits A and B that you want to store in a one-time memory, you should choose one string S to be a uniformly random pre-image of A, and then choose the other string T to be a uniformly random pre-image of B. You put these into the leaky string one-time memory, and then you let the adversary decide what he wants to do. And if he decides he wants to learn A, then his honest behavior should be to simply learn the string S and then apply the function F to get the bit A. Okay, so this is the normal way of using a hash function. This is a normal way of using a hash function. I guess there are many, many things that people do with hash functions. But, okay, so here's the notion of security that we can prove. So this is that with high probability over the choice of F and G, we have the following security guarantee for every LOCC adversary. Now, for every LOCC adversary, there exists a binary random variable C, and the purpose of this random variable is to somehow indicate which which of the two messages is actually going to remain secret, because they can't both remain completely secret from the adversary. Okay? But so in the case where c equals 0, we claim that the first message A remains secret. And we show that the min entropy of A is actually close to 1 with only an exponentially small amount of leakage, exponentially small in k, the security parameter. And if c equals 1, then we show that it's the second message that remains secret. Okay? And yeah, the smoothing parameter is exponentially small as it should be. This random variable c comes from entropy splitting, so it's sort of a it comes naturally out of the machinery for proving this. And the key thing is that the adversary's strategy can actually depend on f and g in this setting. Okay, so yeah, so this slide, I'm sorry, it's sort of a bit technical, but it's basically saying that this is actually a very good single-bit one-time memory. So now the way you prove this is kind of, so the way you prove this, you can proceed in a few steps. So to start out with, I'm just going to describe a simple calculation you can do, which doesn't really prove anything useful by itself, but it will be a useful tool. So the idea is to fix some possible measurement outcome that the adversary could obtain. And suppose that this is fixed first, and then we choose the hash functions at random. We want to claim that then with high probability that this is secure. And so we're really doing things in the wrong order, because in the real construction we choose the hash functions at random first. But let's just do this as a calculation. So, yes. Okay, so from the security property of this string one-time memory, we know that those two hidden strings, S and T, have some amount of uncertainty. By entropy splitting, we know that we can always pick one of those strings. Let's say it's the first one, S, and we know that it has some uncertainty. And so now we want to bound the bias of the first bit A in this situation. And we call that A equals f of S, the hashed value of S. And so we can write this as the expectation of -1 to the bit A in averaging over the values of the bit A. This is just one way of measuring the bias. And so if the bias is 0, then that means that A is a uniformly random bit. And then if we write this out, we can write this out summing over the possible values of the string S. And so -1 to the A equals -1 to the f of S. And so this expression is a random variable that depends on this random function f that we've chosen. And in fact, it's a sum of R-wise independent random variables. And so it sort of obeys some sharp concentration phenomenon. You expect it to concentrate sharply around its expectation value. And so if these were fully independent random variables, then we could use Hofting's inequality. And it turns out that for R-wise independent random variables, where R is polynomially large, there are actually similar bounds that give us similar behavior. And so we will simply try to use these bounds. Now to use these bounds, we need to estimate the variance, or upper bound the variance, of this sum of independent random variables. And so that upper bound, a natural upper bound for this, is the sum of the squares of these probabilities that appeared in this part of the formula. And so this is sort of by definition 2 to the minus the Rényi entropy of S conditioned on these other events. And this we know is small by the security property for the string one-time memory. Okay, so there's this sort of straightforward way of connecting this to the security property for this leaky one-time memory that we started with. Okay, so this is nice, and so what did we really do here? What we did was we proved security for a single measurement outcome that the adversary could obtain. And so the way we can actually prove security in the more general situation is to use a covering argument over all possible measurement outcomes. So we construct an epsilon net for the set of all possible measurement outcomes. Now, since we're in this isolated qubits model, the adversary can only do LOCC measurements, so his measurement outcomes can all be written as tensor products. And so we only need to consider these tensor product measurement outcomes. And so the number of these is exponential in k, but it's not doubly exponential in k. If the adversary could do entangled measurements, then it would be doubly exponential in k. Okay, and so this turns out to be very helpful. So this means that actually the set of possible measurement outcomes is quite small, and when we do this calculation that shows security at one point, the failure probability, we can make it exponentially small in k. And so it's actually good enough to simply do a union bound over this set. Okay, so that, yeah, and this is the sheep. So that's not really what the set looks like, but I don't think, it doesn't have a good representation in 2 dimensions anyway, so whatever, So you can do this union bound over the set, and so now you proved that in fact the scheme is secure simultaneously for all measurement outcomes in this epsilon net. And then the last thing you need is some kind of continuity argument to show that in fact it's actually true at every point in the set, because small perturbations of the measurement outcome don't really change the adversary's knowledge very much. Okay, and so this last part I'm not going to try to describe to you because it's kind of messy, but it's not, there's nothing terribly deep going on there. Okay, and yeah, do you like this color? And anyway, this PowerPoint only has so many colors you can choose for a sheep. So, okay, so let me take a step back now. So I just described a way of doing privacy amplification in this isolated qubits model. And the point of it was to take kind of a lousy construction for a one-time memory and so we had a leaky construction, and the point was to stop this information leakage. And so this is sort of meant to be one step closer towards constructing proper one-time programs for which you really want ideal one-time memories. And unfortunately, this doesn't go all the way there. So the natural question is whether you can build one-time memories that achieve some composable notion of security. And so roughly speaking, intuitively what this means is that there has to be some way of taking the adversary's information that he gets from attacking the real one-time memory and being able to simulate it using a simulator which has access only to an ideal functionality, an ideal version of the one-time memory. And so this I think is an interesting question. Is it actually true that you can simulate these measurement outcomes that the adversary obtains without actually ever having qubits, with only having an ideal one-time memory? And it seems plausible to me, but I don't know how to prove it. So I think this is an interesting question, and it would be nice to know this. Now, so I'm running out of time, so I'm going to actually skip over the other part of the construction. But let me just briefly show this one slide. So essentially, the key to doing conjugate coding securely is in choosing this error-correcting code C. And so the way we've set it up, so it's clear that C should have to approach the capacity of some channel, which represents the honest user's information. And in our setup, it's the Q array symmetric channel for some large value of Q. It's also clear that for security, C should be unstructured somehow, in the sense that decoding C should be some kind of complicated, highly non-local operation involving many qubits at a time. And one way to formalize this is simply to let C be a linear code over GF2. And this is the notion of unstructured which appears in these security proofs. This probably isn't exactly the right notion of unstructured. And if there's some better way of expressing this property, maybe then one can get better security proofs. And lastly, C should be efficiently decodable. And there are techniques, pretty standard techniques in coding theory that can produce these kinds of codes. And so, yeah, and so the security proof uses an entropic uncertainty relation in kind of a clever way, and maybe that is a topic for another time. So, okay, so finally, I just want to mention another open problem. So it would be nice if we could replace this isolated qubits model with one that is a closer match for the actual physical devices, because as several talks have already mentioned, there are ways of generating entanglement between NV centers and between different kinds of solid-state qubits. And so the real situation is that one can generate entanglement in these kinds of systems, but it tends to be noisy and it's difficult to entangle large numbers of these qubits at once. And so one can try to model this also, maybe by saying that all entangling operations are noisy, or by saying that the adversary can apply a shallow quantum circuit. And so it's interesting to ask whether these constructions that are proved secure against LOCC adversaries can also be secure against these slightly more powerful classes of adversaries. And if this is true, then this would also strengthen the argument for actually building these devices. And with that, I guess I should come back to my original point that so I think there should be a lot more to say about this, because as you may have seen, these constructions that are known so far are really not so complicated. We're just doing privacy amplification in the simplest possible way, using a random-looking function. And these LOCC adversaries have a lot more structure in them. And likewise, the choice of error-correcting code that we use to build a one-time memory also imposes some additional structure. And so it seems like using that, if we could use that structure, we should be able to get much better security guarantees. So this is a question for theorists, and then, for experimentalists, for experimentalists, I guess. So I guess for experimentalists, it's less clear how exactly this connects with what one can do currently in the lab, but I think it's a kind of a useful goal to keep in mind as something that maybe one might be able to do someday. And I'd be very happy to actually get feedback about this point. So with that, let me finish.
Concerning the composability, have you thought about modeling the ideal isolated qubits as functionalities in the UC model? Because then you could, at least the one-sided extractability you would immediately get, because the simulator knows what's in the qubit, like the complete instruction, and he will also know the measurement results, which might allow him to extract the C, which would give you everything you need. Have you tried that?
So I've thought a little about this. I know Fang Song has thought about it, and I think we were running into some technical issues with it, but so I don't know exactly what was the situation with that. So I'm afraid I don't know. We tried this and ran into some technical issues, but I'm not sure that we really got to the bottom of it.
So in QKD with a full quantum adversary, we know we can't do privacy amplification deterministically. Right? It needs to be done after the transmissions happen. Is it clear what's sort of the minimal assumption or restriction that's placed on the adversaries that allows you to, to make it deterministic here?
Let me see. So I think it's not completely clear. I think this deterministic privacy amplification, I think it would also work if the adversary can apply some polynomial-sized quantum circuit. I think the same kinds of arguments could work. And I think there are also results on deterministic extraction for computationally bounded sources, just in classical cryptography. So I think in this kind of situation, deterministic extraction is possible in a pretty general sense, but I'm not sure exactly where is the boundary. Yeah, sort of between these computationally bounded situations and the general situation where the source is computationally unbounded.
I also have a quick question. So what goes wrong in the proof if you have constant number of qubits or even logarithmic in your security parameter than one single qubit?
Let's see. Sorry, in which part of the proof, or sorry, like in which part of the construction, rather than having one?
If you assume that your adversaries not only have a single qubit but a constant number of qubits and they can do whatever they want.
Oh, I see. If the adversary can sort of
Yes.
like do joint measurements on logarithmically many qubits. So what goes wrong is that. So the way we were arguing security was to say that, so in the one-time memory, it has many qubits, and there will be a subset of them that are in a maximally mixed state. And so when the adversary measures these, he learns essentially nothing about which basis choices were used to prepare these qubits. And so we can show that the adversary somehow falls behind during this stage of the attack. And to make this argument, we needed to reason about a partial measurement outcome. Somehow we needed to define some notion of the adversary's attack on this subset of qubits. And if the adversary is measuring larger subsets of qubits and is possibly generating some entanglement, then it's harder to separate out this subset from the remainder. So I think, this sort of seemed to be the issue.